This video looks at how to do implicit differentiation, and it's just a short video because this isn't a very big part of our course, but it's important to be able to do it all the same. So implicit differentiation is useful because it allows us to differentiate different types of equations, specifically relations that aren't written in the form y is equal to. For example, this equation x plus y equals 5 isn't written in the standard y is equal to format that we were so used to seeing with differentiation, but we can still differentiate as it is. So in this case, to get our derivative, we're just going to differentiate each term as we come to it. Now, let's have a look. We know what happens with x when we differentiate it. We just get 1. So that's fine, nothing new so far. But when we get to y, what do I get when I differentiate y? Well, when I differentiate y, I get dy dx. I differentiate the 5 at the end and I get equals to 0. My goal in an implicit differentiation question is still to find dy dx is equal to. So I'm simply going to have to rearrange this line now to get dy dx. So in this case, dy dx is equal to minus 1. Let's look at a second example. So this time we've got 3x squared plus y squared minus 4x equals 0. Okay, so starting off, I'm going to differentiate my first term, 3x squared. When I differentiate 3x squared, that's just like normal. The 2 comes down in front and multiplies. I end up with a 6. I reduce the power by 1, so it's just 6x. Next, I've got the y squared to take into account. When I'm differentiating y to a power, I'm effectively using chain rule. So what I'm going to do is bring my power down in front and reduce the power by 1 like I normally do. And I can write the 1 in, or I can leave it out if I like, because it's not really making much difference. But I must also remember that I then need to differentiate the y. And of course, y differentiates as dy dx, and I multiply that by that 2y. I differentiate the minus 4x and I get minus 4, and 0 just differentiates as 0. And now I just need to get dy dx is equal to. So getting the 2y dy dx term by itself, first of all, that's equal to 4 minus 6x. And then I'll write dy dx equals 4 minus 6x over 2y. And if you like at this stage, you can simplify a little bit to give 2 minus 3x over y. Here's one final example. Sine y plus x squared minus 3x equals 0. So I'm going to, first of all, differentiate sine y. And of course, I still need to use my rules for trig differentiation here. So I need to have power, ratio, angle when I'm differentiating trig. Okay, so there isn't a power in this case, so I can move on from that straight onto ratio. Differentiating my ratio here, sine differentiates to give me cos. So that's cos y, but of course, I must differentiate the angle then, which is y, and that's going to give me dy dx. And then I continue on to differentiate the remaining terms as normal. So x squared differentiates to give 2x, minus 3x differentiates to give minus 3, and I've got my equals 0 on the end. And again now I simply want to get this in the form dy dx equals to finish up. So I'll first of all get the term including dy dx by itself. So that's minus 2x plus 3. And then finally dy dx is equal to minus 2x plus 3 over cos y. We'll mostly encounter implicit differentiation when we're differentiating inverse trig functions. It's a skill that we need to have before we can go into that topic. So make sure that you practice your implicit differentiation before you go in to your inverse trig functions, particularly questions like example 3, where there's a little bit of trig. We don't tend to encounter difficult implicit differentiation questions, like I said, but we do need to have the skill.